Okay, so how is everyone today?
Very well.
All right. So, today is what, the 12th? Okay. So today's topic is square root.
Did the quotient remainder stuff get posted then?
It hasn't been posted yet. You mean the quick quotient and remainder instead of the.
Over and
No, that one hasn't been posted yet, but it'll be posted hopefully today.
okay, because we didn't quite finish it, remember?
Did we not?
No, we didn't finish it.
Well, how far did we get?
We did the first part. Where you,
If it's posted, I think we're all happy with it. As long as it goes up.
We'll fix it with whatever's missing. I'll have a look at it and write some written homeworks to fill in the gaps, because we're going to do square roots today. All right. Fine. Square root. So we're going to assume we know how to multiply and divide in the reals. But we don't, and if we know how to multiply and divide, obviously we know how to add. So we're going to assume that we know that, but we don't know how. But don't know how to do square root. Okay, so the idea that makes this all work is as old as antiquity. Okay, so the name of the main idea, it's called the Babylonian Method. Now, for those of you who are interested in history, you should know that yes, I believe it is a fact that the Babylonians used this method. That is true, but I don't think it is in fact true that they invented it. I think it was invented in at least 2 independent places and before the time of Babylon. I think that's the actual historical fact. Okay. So, well, suppose that we have some number b, and it's more than 0, and we want to compute the square root of b. So we want to compute the square root of b. The way that we're going to do it is we're going to come up with a guess. Suppose we have a guess. And we'll call this guess A. And of course, because, even though we don't know how to compute square roots, we are intelligent enough to know that surely whatever our guess is, we're going to choose a positive guess. So we'll have our guess is positive. So now there's 3 possibilities concerning our guess. It's either the case that our guess is too small, or we have guessed exactly correct, or our guess is too big. Right? And there's no other possibilities. So let's consider the case. Suppose that A is too small. So that is to say that A is less than the square root of B. Now, we're using our sort of omniscient knowledge to know that A is less than the square root of B. We don't actually know the value of the square root of B. Suppose that this is the case. Then I'd like for you to consider the following. B divided by A. So we know how to compute B divided by A because we said that division is one of the things that we know. So we can compute this. How does this? Compare to the square root of B. That is to say, our guess is A. We know the value of B. That's the thing we want to compute the square root of. And we're currently in the supposition that we have a guess, but it's too small.
So that will be greater than the square root.
Okay. So let's have a look. Can you explain why?
Because B divided by root B is root B. So if you divide B by a number greater than root B, it's going to be less than root B.
Okay, so let's write it out carefully. I agree with what you said. So B, in the first place, we know, even though we don't know the value of the square root of B, we do know that it is the case that B is equal to the square root of B squared, right? Surely that, we know that that's true even though we don't know the exact value of the square root of B. Which means that B, of course, is equal to the square root of B multiplied by the square root of B. All right, so now let's divide both sides of the equality by A. So B over A, this should be equal to the square root of B multiplied by the square root of B over A. Right? But suppose that, so what do we need to do now? So how can we get it figured out? Well, let's think about it. Somehow we need to simplify this. And we need to get this, B over A, to be compared to just a square root of B. So what I'm saying is that, for example, if we could cancel a square root of B and an A, and just leave a square root of B, that would be excellent. So how can we do it? Okay, right. Because this is the case. Because this is the case, we also we can say what?
It's greater than if you replace the A with the square root of B.
Right. So we could write it like this. As an intermediate step, we could say because A is less than the square root of B. If we take this inequality and divide both sides by A, then we would have that 1 is less than square root of B over A. So square root of B over A, square root of B over A is more than 1. More than 1. As a result, what can we say? So in particular, this is square root of b over a right here.
B over A is less than square root of
Other way around, right?
yes.
Because the statement is that you have b over a is exactly equal to the square root of b multiplied by the square root of b divided by a, but that factor right there is more than 1, so if we replace it with 1, then we have just 1 multiplied by the square root of b. So in particular, this factor right here, because it's more than 1, and if we replace it with 1, then it changes from equality to inequality. All right, so now what I want you to see, therefore, we have a guess. Guess A is too small. And B over A is too big. Therefore, we don't know the value of the square root of b, but we do know that the square root of b has to be in the interval a to b over a. It's got to be in there. So, this is, I hope you're getting sort of an echo of the guess the natural game. So when we were able to establish that the natural that we're searching for is in an interval, then what's the next guess that we choose? The midpoint. So we could make a better guess. So therefore, a better guess and so, because we're not doing anything too rigorous yet, I'll say might be. The midpoint of this interval might be a plus b over a over 2. So now, where computers are concerned, the division by 2 is a triviality, so that's easy. But we are assuming that we can compute b over a. So we're assuming that that's possible. Interesting. Okay. That's if we have a guess that's too small. If our a was too small. Suppose that a is in fact equal to the square root of b. But of course, that's unbeknownst to us. We don't know that. Okay. Then, what can we say? What can we say about this formula? Well, let's figure it out. So notice that a plus b over a over 2. In the specific case that a is equal to the square root of b, well, that's equal to the square root of b plus this b over the square root of b over 2. And what is b divided by the square root of b? Square root of b. So there's 2 of them, so that cancels and you just get the square root of b. So that would mean that if we use that formula, a plus b over a, and then divide by 2, the midpoint of that interval, to get a new guess, if we happen to have guessed correctly in the first place, then we'll still have the correct answer, right? So like, for example, we know that the square root of 16 is 4. So suppose that we don't know that for a moment, and our guess is 4. Then 4 plus 16 over 4 is 8. And then divide by 2 is 4. So this formula maintains, if the answer was correct, it doesn't move away. What's the last possibility about our guess? Right. Suppose that we have a guess, and it is too big. And again, we don't know the value of the square root of b. I'm just speculating what would occur. Well, if a is too big, let's see if we can find out. Let's see if we can establish. Can we show that b over a is too small? So can we show it? How do we do it? Same way, right? The only real distinction is that instead of writing square root of b over a more than 1, it'll be the case that square root of b over a is less than 1. Okay, so let's just do it real quick. Can we show that that's the case? Yeah, sure we can. Right, because, well, we know that, of course, b is the square root of b multiplied by the square root of b. So b over a is the square root of b multiplied by the square root of b over a. And again, we see this factor right there. And from a more than square root b, we can establish that 1 must be more than square root b. Oh, did I just run out of ink? These pens are a little bit fidgety, but they're the ones that show up best on the projector, so I run with it. Okay. 1 is more than that. So that means that b over a is this factor times the square root of b. And this factor in red is more than 1. And it's less than 1. So that means that to get b over a equal to square root of b, we have to multiply it by a small thing. So we have to make it smaller. As a result, we can say that b over a must be less than the square root of b. Therefore, we've established that the square root of b must be in the interval, what? B over a to a. Now that's a different interval than the other one because, well, it's just that they're in the other order. But in this case too, we were able to establish an interval in which the square root must reside. So again, we could use the midpoint. Therefore, C equal to, you could write it B over A plus A over 2, like that. But I'll commute the numerator so it's the same as the formula in all three cases. So what I want you to see from this is that therefore, given a guess, A, which must be positive, given a guess positive A, C equal to A plus B over A over 2. I'm gonna write in red might be. a better guess. So now, in actual fact, hopefully you'll take a numerical analysis class and you'll be able to establish that that might be is not necessary. In fact, you will obtain a better guess, but unless you happen to be exactly on the correct answer in the first place, in which case you won't move. So it's a better guess. So let's see. Let's see this kind of idea in action. So, for example, suppose that we want to compute the square root of 70. So we want to compute the square root of 70. So the first time I do it is going to be tedious in the extreme. Then I'm going to ask if someone can tell us a better way we could do it. Okay, so I'm going to say that my initial guess is A0 is equal to 1. Maybe it's 1. So we know that in actual fact that 1 is too small. Okay, fine. Well, let's figure out. I guess I'll just write A. It doesn't matter so much. So let's make a table of values. So we're saying that our first guess is 1. Now, in actual fact, we can use the calculator and say, well, we know that the square root of 70 is in fact, to several decimal places, about 8.37. Okay, so now, what will be the new value of A after we use that formula on the previous page? So what do we need to compute? Right. So what we need to calculate to get to this position is 1 plus 70 over 1 and then over 2. So that will be the guess. Okay. Okay, that gives 35 and a half. 35 and a half. All right. Then to get the next guess, the update formula would be 35 and a half plus 70 over 35 and a half, and then divide that by 2. All right. If we do that, then we get 18.74. That's just 2 decimal places. If we do the formula again, we get 11.23. 11.23. If we do it again, 8.73. If we do it again, 8.37. Of course, we don't know the correct answer. So if we do it again, we get 8.37 again. And on my calculator, I didn't get the same number twice. I'm just saying that when I took the number and rounded it to two places, it was the same, 8.37. So I hope it's obvious, but how can we tell that we've gotten close enough?
Equals A to a certain decimal place?
Right. So there's no change now. So in a sense, we stopped moving. Okay. So that took 1, 2, 3, 4, 5, 6, 7 iterations to figure it out. So I claim that as a human, you can kind of tell me a better way to go about doing this. Like if you were going to start, like if it was your job to compute square roots, say, and someone said, okay, now I need the square root of 70. Would you have started with 1?
No, I started at 64.
Well, you need to start with a good guess. So I claim that you can tell me relatively quickly 2 integers that the square root of 70 must be between.
64 and 81.
You don't mean those numbers, you mean 8 and 9, right?
8 and 9, yeah.
Good. So surely it's between 8 and 9, right? So let's try it again. Let's try it again. But now let's make the initial guess a little better. A equal to, I'll say 8. A equal to 8 because after all, 8 squared is less than 70 is less than 9 squared. So surely the square root of 70 has got to be between 8 and 9, so it's got to be better to start at 8. All right. So if we do that, the first update gives us 8.38. Wow. And the second update gives us 8.37. And the next one gives us 8.37. So do you see that that having a high quality initial guess, that's useful, right? It would have been even more pronounced if we had been computing, instead of the square root of 70, if we had been computing something like the square root of a billion. It would have taken a while to finally start getting close. Okay, but you know, as it happens, a billion is the square root of a billion. It's got to be between 2 integers, right? I don't know which ones. Let's say, well, a billion is 10 to exponent 9, right? So it's got to be between 10 to exponent 4 and 10 to exponent 5. So 10 to exponent 4 would be a good initial guess, right? Yes?
You always want to go with the floor guess?
We're going to make it explicit in a moment, but the only purpose here is just to show you that if you have a way to make a high quality initial guess, then you should do that.
You said computing time?
Yeah. Okay. So good. So let's make it a little more formal for a moment. Let's define I'll call it B from the reals. Well, I'll say real I'll write star to real star, and by real star, well, I mean the non-negative ones. Real star is the set of all x in the reals such that x greater or equal to 0. That is to say, real star is the domain of the square root and also the image. All right, we want b. We're gonna have b to be that update formula. But in fact, we need to be a little bit, just slightly careful, because when we were talking about that update formula, a plus b over a over 2, we were assuming that the b in question was positive, but now the inputs don't need to be positive. Okay. So the formula for b of x is in fact going to have two cases. One of the cases is, no, we need it needs to have, sorry, the input actually needs to be r star cross r star. It's two of them. Because one of them is the thing you're trying to compute the square root of, and the other one is your current guess. Okay, so this parameter is you're trying to find the square root of b, and this one is your current guess. All right, so the formula that we discussed 2 pages ago is good to go. So then we could say that the update will be a plus b over a, and then over 2. And notice that we established that formula works without regard to whether or not your current guess happens to be too small, the same, or too big. But in fact, this we can do better than this by putting a clause up here, because there's one special case. Sorry? Well, even when the answer is correct.
0?
Right. So yeah, if the input is 0, what's a good guess for the square root of 0? 0. Okay, good. So we're going to say 0 in the case what? B is 0. And then this otherwise.
Do we not do anything for when like A is exactly B?
No. So all that this thing does is just tells you what your next guess should be. So that's all that it. That's its only.
It's only job.
Its only job. Now, let's define. Let's define S from R star cross R plus to R. And in this instance, what I mean by R plus is that this is the subset of the reals where these things are positive. So in this notation, R star permits 0, but R positive does not permit 0. Conceptually, what we want is we want S of b and epsilon to compute the square root of b to within epsilon. So that is to say that you could say, well, I want to know the square root of this number to within, say, 0.01. I want to know when that's the case.
You said within epsilon 0?
Within epsilon greater than 0. So what I'm saying is you want to detect, you want to continue guessing until until you're sure that you're within epsilon. Okay. Well, in order to do this, we're going to need an auxiliary function. Can anyone see why we're going to need an auxiliary function?
Yeah, because we have to have the guessing.
Right. Somehow you've got to keep track of whatever the current guess is. Right? So we'll define S of b and epsilon to be just S0 of b epsilon, and just to make things easy at first, we'll write 1. So this will be the initial guess. So right now, to make things simple, we're saying that we're always going to start out by guessing that the square root is 1. That being the case, we're going to need a definition for S0. So S0 of b, epsilon, and a. All right. So, what can we do? So there's going to be 2 clauses. One of the clauses is going to be that we have found the answer. And that means that we found an answer that is within epsilon.
So like b minus a less than epsilon?
Something like that. No, not b minus a less than b. B is the number we want to compute the square root of, and a is our current guess. So like if we were computing the square root, if we wanted to compute the square root of 70, then b would be 70, and we'd exit when a gets close to 8.37. So those 2 numbers will not be close generally. So there's going to be 2 clauses. One which is saying that we're done, and one that's saying,
Guessing.
yeah, we need to continue. All right. So I'll start out by saying that for all clauses, I'll say let C be equal to whatever the next guess is, right? So
So a plus b over a.
no, not that.
Oh.
We've got a nicer name
Which
for
is b,
the next guess.
b, comma, a.
Right. Capital B of B and A. Of course, the reason why I chose the name capital B for the function that computes the next guess is why? Babylon, right? But do know that, you know, if you're into history, there's a little bit of a lie there.
So
Good.
it's actually inventable.
I can't remember off the top of my head. All that I do remember is that, in fact, it wasn't the Babylonians.
Made famous by, but not invented.
I'm sorry?
Made famous by, but not invented.
Yeah, that might be. Yeah, I think that sounds right. Yeah. Okay, so let C be this. So this is something for all clauses. So how can we tell that that we're done?
A minus c.
Okay. Okay, so the current guess minus the next guess less than epsilon. So you're saying that's how we tell when we're done? Okay.
Or the magnitude.
That's better. Right, which is to say that this one. right? So when the absolute value of the difference of these two is less than epsilon, that means that we must have gotten close enough. So what's the answer when this is the case? Well,
Or C.
C would be even better, right? So why is C even better?
Because it's the next guess.
Because it's the next one, right? So use that one. Okay, so that's the condition that says that we're close enough. We made it far enough. So now we need an otherwise. Right. So this is the clause where, oh, there's more work to do. So we need to recurse. So what? Of B, epsilon, and what?
C.
C, right? So the idea is kind of simple-minded, right? It's, well, at every step you compute a candidate. You check whether or not this candidate is within epsilon of the previous candidate. If so, then the newest candidate is the answer. Otherwise, continue. Okay, so let's track the state here of this function for just so we can see it work. So, for example, let's compute S of something relatively small now. So how about 10 and 0.01. So that is to say we want to compute the square root of 10, to within 0.01. All right. So the first thing that this function does is what?
Call S of 0.
S0. So it does, okay, S0 of 10, 0.01, and the initial guess is 1. All right. So that means that we need to compute a C because both clauses use the C. The initial guess is 1. Okay, so then the C candidate is C equal to 5.5. So the difference between, I'll write, the absolute value of A minus C here. So A minus C in absolute value, in this case, is equal to what? 4.5, right? So is 4.5 small enough?
Yeah.
It's not. So we continue to S0, 10, 0.01, but now our guess is 4.5. By the way, the square root of 10 is about 3.16, right? So we went from 1 being an underestimate, and we jumped past it to 4.5. Okay. So no, not 4.5. I made an error here. What's the error? That's the absolute value of A minus C, right? What argument does this need to be? C, right? So that's my error. Okay, so in fact, so what I said is still true. We still jumped ahead, right, of the true answer. All right. So in this case, C is 3.66 ish. So then 3.66. We'll just eyeball it. Is that within? A minus 3.66, is that within 1/100th? It is not. Fine. So then we must continue. So S0 of 10, 0.01. The next guess, so this one is about 3.66. The next guess is 3.20. And I'm rounding these to 2 decimal places when I'm writing them down, but not on my calculator. So if you're trying to reproduce my answer, it might be slightly different because I'm doing some strange rounding. So the difference between these two numbers now is not within 1/100th, so there's more work to do. So now we have 3.16. The difference between these two numbers is still more than 1/100th, so there's more work to do. .16, and again I'm just rounding to 2 places. So now the difference between them is less than 100th. So what's the answer? Yeah, approximately 3.16. So the calculator is currently reading that 3.16 blah blah blah. For those of you who are wondering how I'm doing that with my calculator, the way I'm doing that is I start out by typing, I do 1, and then I press enter, because the effect of pressing 1 and then enter. What if you do? What happens when you do that at the MATLAB command? It doesn't make an error.
It does not.
It says, well, in particular, it does something. It says A and S equal 1, right? So the net effect of this is that the calculator stores the value 1 in the slot that can be referred to as A and S. And then in the calculator, I type in the following formula. I type A and S plus 10 divide A and S, and then divide 2, and then I just keep pressing enter, 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 enter. That's how I'm, because when you type this, it calculates this and then does what with that result?
So is that as an
Stores it in A and S, right? Okay, nice. So any question about this? Okay, so now that technique, what we just did, can compute the square root of any number whatsoever. That technique will always converge, no matter what number you choose. Millions, billions, trillions, but it could take a lot of steps, conceivably. The reason why it could take a lot of steps is because guessing 1 is not an excellent strategy. Okay. So what we're going to do is we're going to come up with a better strategy for coming up with a guess, an initial guess. And so we want a fast way for MATLAB to have an initial guess. Now, for humans, when the numbers are relatively small, and if you're a math major, right, all math majors should know the squares of integers up to like 25. That should be just, really, that's just something that you should just know, right? Like you just know all of them. Similarly, it would be quite good for you to know all the powers of 2, preferably up to 2 to the 16, but at least up to 2 to 10. That's just something that you should just be able to rattle off immediately. Is 10, 24? Yeah. What's the biggest number that can be stored in 10 bits? Well, 1023. Right? Because you want to be able to store 0, right? Okay. So that's just something you should know. So for a human, when we said let's compute the square root of 70, we came to the conclusion that 8 would be a good place to start. The reason being is that 8 squared is 64, and 9 squared is 81, 70 is in between those two numbers, so 8 would be a good place to start. But here's the thing, is that when you want to compute the square roots of numbers, there's too many numbers, there's too many possibilities. We don't want to traverse just the squares. So that is to say, we don't want to check, is it between 8 and 9? Is it between 9 and 10? Is it between 10 and 11? We don't want to do that because square doesn't grow fast enough. The reason being is that the Babylonian method that we're talking about, we haven't established this in class. Hopefully you'll take a numerical analysis class where you do establish it. But every time that you run the B function and come up with a new update, the number of bits that are correct doubles. So if you have 1 bit that's correct, then the Babylonian method will return to you a number that has 2 bits that are correct. If you have 8 bits that are correct, the Babylonian method will return to you a number that has 16 bits correct. So the thing is that on the computers that we use in class, in the lab, and the computers that you all have right there, they represent numbers using, depending on specifics, between 64 and 128 bits. So if you have 1 bit correct, how many times do you need to double until you have, say, all 128 bits correct? 7 times. That's how many doublings you need. So you only really need to do it 7 times if you have 1 bit correct. If you have 2 bits correct, then you only need to do it 6 times, right? Okay. So here's how we're going to do the initial guess. So recall the following. That x to n to m is, of course, x to nm. Right? When you iterate exponents, you can do that. So in particular, we know something very easy, that the square root of x to 2n when x is positive, non-negative, will be what? X to n. That's just a restatement of that x to 2n is x to n squared. Okay, so we're not going to consider sequences of integers and ask for and square them. In fact, we're going to compute powers of 2 and square them. Okay. So, for example, suppose that we want to compute, say, the square root of, how about 275? The square root of 275. What we're going to do is we're going to compute sequential powers of 2 and have them squared and do it like the following. So we're going to ask, well, the first power of 2 that we'll consider is 1, and then 1 squared is 1. So I'm going to ask, is 257 less than 1? Nah, it's not. So that's not going to, we're not going to use that one. The next power of 2 is 2. Then we're going to square that and get 4, and then ask, is 275 less than 4? Nah. So let's use the next power of 2. The next power of 2 is 4. 4 squared is 16.
Is that 1 ring 1?
That's a 1.
Is it 2 to the 1?
2 to 0.
What this is, well, let me write it like this. 0, 1, 2. This is n. This is 2 to n. And this is 2 to 2n.
Okay.
So the 0th guess was 1. Like, what was that? So the next guess would be, well, the next power of 2 is 8. And 8 squared is 64. So is 275 less than 64? Nah. All right, the next guess, the next power of 2 is 16. 256. Right? Okay. Well, is 275 less than 256? Nah. All right, so then the next power of 2 is 32. 32 squared is 1024. Is 275 less than 1024? Winner, right? Winner. So it doesn't really matter. Let's think about this. The square root has the tendency to overestimate. Let's think. Can I think of so now what I'm trying to, what we've established is that the answer has to be in this interval, right? That's what we know. And so now I'm trying to see if there's any reason why we should pick this one or that one. Let's think about it. They both have nearly a bit correct. I think we need to choose this one. We'll choose this one. So we'll say that this one is the winner.
And this is
Winner.
B, the first.
Winner because we've finally established that 275 is less than 1024. So we finally hit the wall right here, so we say, that's the one. Okay, as a result, yes, we're going to take 256 to be the initial guess. So the initial guess is A equal to 256. And then we use that as input to that procedure. Okay, so now let's see if we can write a function that does this.
That guess is our best guess.
Yeah, that comes up with the initial guess.
We don't want the square root of 256.
Thank you. Yes, of course the answer should be 16, not 256. Thank you.
So A is equal to the square root of.
Right. So what I mean, I guess really what I meant is that this iteration was the winner. That iteration was the winner, and the square root that we want is that one. Good. That's our initial guess. So can we come up with a function that does this? Okay. So we'll define. How are we doing on time?
We've got like 3.
Okay. We'll define L from the non-zero, or the non-negative reals, whoops. And we'll just say to the non-negative reals. In fact, it's only going to produce integer guesses, but that's fine. We're gonna do this. This is the thing that computes our initial guess. We're going to need an auxiliary function. Why are we going to need an auxiliary function?
Keep track of the guess.
To keep track of what the current guess is, right? Okay. So we want to compute the square root of b, but we need an auxiliary function, so we'll call it L0 as is our usual usual strategy. The initial guess here is what? 1, right? Well, 2 to the 0. Right? Yeah. So we'll say that it's 1, which is 2 to the 0. So then L0 of B, and what name do you want to give to our guess? Okay, A. We'll use A. Okay, so now what we want to do is we want to see have we found a winner? Really, that's not really the question. It's really like have we found a loser, right? Have we hit the wall yet?
Have we gone over?
Have we gone over? Okay. How do we tell when we've gone over?
When your guess is greater than what your fee is. So when
It's
C-
not when the guess is bigger.
the guess for your your starting point.
When 2 to that number is greater.
This right here, that A is this row.
Oh, okay. So it's when A squared.
Right, A squared. So if it's the case that A squared, so what do we need to say? A squared is greater than B. If A squared is greater than B, then we hit the wall. We went too far, so what's the answer?
A squared minus 1. I don't know.
It's not A, right? So A is this number, is this sequence of numbers, 1, 2, 4, 8, 16. So in the case of 32, we'd say 32 squared more than B. Then we said that the answer
Is
A over
divided
2.
by 4.
A over 2. The previous power of 2, right? So like when we got here, A was 32, and then we squared 32 and said, oh, that's 1024. But that's too far, so the answer must be the previous power of 2, 32 over 2. So that's, we're finished. So otherwise, we have more work. Otherwise what?
L of B,
Do we use the B?
L0 of B and what?
2.
2A. So now, this thing right here, the reason why I chose the name L, and we're out of time, so I just need to finish this thought. The reason why I chose the name L is because what actually happens on your computer is that your computer takes that number and performs a calculation called a lookup in a lookup table. So it's trying to figure out what's the best initial guess for a number that's like this. And that's called a lookup, which is why, and it's performed upon a lookup table, which is why we called it L. Okay, so finally, the way your computer actually works, is it doesn't actually compute a loop. What it actually does is it has a Babylonian circuit, and on a 64-bit computer, it's got a cascade of 7 Babylonian circuits in a row. So it doesn't try to do 1 or 2 or 10. It does exactly 7 every time. And it's able to do that in one clock cycle, if you can believe it. Amazing. So have a nice day.